about commensurate order systems. To find the solution for this kind of systems, we can use two of the properties of Laplace transform. For this kind of Planck model, or for this kind of transfer function, there's only one term there, one fractional term in the denominator. We can find the analytical solution of it easily. So this is the standard form for this one, standard transform of this one. And we can also interpret this part like if the transfer function is given like this, then this one should be the impulse response of this system, right? We can take the inverse Laplace transform to it directly. So this is one of the important properties of Laplace transform, and with the use of it, we can consider how can we find the analytical solution for commensurate order systems. For the system, we can redefine the system using we think it is called a partial fraction expansion, and to find the other terms in like this, then we can find the analytical solution for the whole system. I will explain that one later to you. And also there is another important property defined like this, where there is S1 or S in the system, and we can see that this part can be considered as the step response of the system, like this. So we can make use of the two terms. And now, how can we solve commensurate order systems? This is the question why we want to solve. This is the problem we want to solve. And the standard form of commensurate order system is usually given like this, where we can see the orders 1 time of alpha, 2 times of alpha, until n minus 1 times of alpha, and n times of alpha. So we can introduce an operator lambda, which equals to s to the power of alpha. And if we have done this, we can easily rewrite the original transfer function like this, which is a standard rational function for the variable lambda. And for this rational function, we can easily perform partial fraction expansion and find that the original transfer function can be expressed like this. If there isn't any repeated poles, we can easily write it like this. However, if there are repeated poles, we cannot easily write it like this. So this is the limitation of the algorithm. And by the use of Matlab function residue, you can easily find R's and P's from this transfer function model. So let's consider examples. Oh well. So with the use of this representation, we can easily write, if we use, for instance, if we want to get the impulse response of the system, we have to use the Laplace transform property like this, and then the the analytical solution of the system can be derived like this, where this is the original transfer function. And if we take the inverse Laplace transform to it, then we will get an analytical solution of the system like this. So this is the analytical solution for commensurate order systems for impulse inputs. And also, if we use the properties we can easily find out that the analytical solution two-step input are given by this. Well, here I used the partial fraction expansion to the original transfer function of the system. So the final result should be something like this. So now I will demonstrate this part by an example. Suppose we have a fractional order transfer function like this. How can we find the step response or impulse response to the system? By checking this system model, we can see that it is a commensurate order system if we assume that lambda equals s to the power of 0.4. So this is the first order of lambda, second, third, and fourth. So by introducing an expression like this, we can easily rewrite the original commensurate order system in terms of lambda. Well, for this term, for this transfer function of lambda, we can easily find by the use of residue function that the partial fraction expansion of the system can be expressed like this. Once we have a partial fraction expansion, if we take the inverse Laplace transform to the form, we will directly find the analytical solution to this part, since it follows from the very important property for input. And also we can find the inverse Laplace transform for these terms. Finally, we can easily find that the impulse response, analytical solution to the impulse response could be written like this. Well, this is the impulse response. Since the partial fraction expansion is given and there isn't any repeated poles, we can use this property to find the step response of the system. So the analytical solution to the step response of the system can be obtained like this. And we can use the Mittag-Leffler functions defined in Matlab to calculate the numerical solutions from it as well. So it has an analytical solution, and also we can use the function to find the numerical solution to impulse responses and to step responses of the system. And it should be noted that for certain approximation in the problem, we have to use indirectly the polynomial MLF function, MLF function. It is slow but it works well.